Okay. Good morning. We're all in together now, including the online world. Kind of chilly this weekend, I guess. Hope we're all having a nice fall, just like Humpty Dumpty. Okay. Right. Couple of announcements. We got a lot of stuff coming up in the next like 2 weeks, so I just want to be clear on some stuff. So homework number 3 for this class was due today. That was on your principal stresses. So hopefully you managed that. Just 2 problems, a little MATLAB fun there. Hopefully we enjoyed that. Maybe some people didn't. I don't know. Different cup of tea. So there you go. I posted a new homework. It's homework number 4. It's on failure criteria. That's 3 problems. So again, not too many. Shouldn't be too tough. One of the problems, actually, you get to use the MATLAB code from your previous exam or your previous homework to just like figure out the principal stresses. So you just punch some numbers in there, and that will help you on your way. So that's posted on Blackboard now. That'll be due next Monday. And then kind of the lab periods here I want to discuss for just a second. This week in lab, we're actually going to do the buckling lab. And this buckling lab will not be due for 2 weeks from this upcoming week. And that's because next week during the lab period, you'll have your first exam for the class. So we'll go through the buckling experiment this upcoming week, and then you'll have 2 weeks to actually write the report. That's because we need a little bit of time to sort of like go through the buckling material in lecture. And also, I don't want you to have to think about getting a lab report in like right before the exam. I think that's a little unreasonable. So we'll give you 2 weeks to do the buckling lab. So that'll be due the week of October 19th. So it will be the 20th for those of you in the Tuesday lab, and the 22nd for those of you in the Thursday lab. And there really isn't much to that lab. We're going to do all the theory in class, so there's no real lecture portion to that lab. So we'll just come and maybe watch the video, and kind of just, it'll be a pretty chill sort of lab section this week, so that'll be nice. Okay, then your exam will be the week after that in the lab time, and the exam will be open everything, and will take about 100 minutes, I'm going to say, for it. All right, so hour and 40 minutes. And the way that that's going to work, I'll just give it to you briefly, but I'll also send this out in writing later, is you'll sit down at your computer at home. We're not going to do it in person. You're going to do it at home or wherever you stay and want to take your exam. I will release the exam right at the lab time, so 10 o'clock on Tuesday or Thursday, depending on the day. And you will just fill out the exam on paper in front of you. You don't need to copy the problem down. You just write like number 1 and you go. Okay. So the exam will probably be like 4 problems. I'm not quite sure yet, but you just fill it out in front of you, blah, blah, blah. And then you hand it in to me just like you'd hand in homework, right? So either scan it or take a picture of it with your phone and send it to me. And that has worked like pretty traditionally well in the past. So I think I'm going to go with that model again. Open everything. So open whatever you want. You want to use notes from the class? Fine. You want to use internet? Fine. Though I sort of advise against that because you're probably not going to have enough time if you just go down the internet rabbit hole. Okay. So just very briefly, those are the things that are happening right now. I do plan to put out like a review worksheet for the exam, probably in the next day or 2, that'll have practice problems related to the material, and I think will be representative of sort of like so those of you that had me in like 2003 in the spring quarter, you saw something like that from me as well. So I'll put those out and give solutions, and you can sort of go through those on your own time. All right. So a lot of stuff going on. Hopefully that's clear. We have a question in the audience, Mr. Caleb. The question is, does the exam cover material on homeworks 1 through 4 or 1 through 3? Through 1 through 4 is the answer. So up to and including failure criteria, I won't have buckling on this exam. All right. Other questions? Okay. Will you have a review session? Possibly. I haven't figured it out yet. I kind of have to make like one other announcement, as I have to kind of make like a semi-emergency family trip to Pittsburgh this weekend. So I might actually miss lecture on Friday. So I think I'm going to have to pre-record that. But more information to come. This is kind of a recent development. All right. Everyone's okay. Don't freak out. It's just, I might have to be gone on Friday. Okay. So that's interrupting my potential for a review session also. Okay. That's enough ado. Dang it. Let's do some stuff. Okay, we just have a little bit left on the failure criteria notes, and then we're going to move on to buckling. So I've posted a new set of notes on Blackboard on buckling, but I just do want to put a cap on the failure criteria notes. So the main failure criteria that we had talked about. And the ones that I will test you on are max normal stress theory. You have max shear stress theory. Which is sometimes called the Tresca. And then you have maximum distortion energy theory. Which is sometimes called the von Mises failure criteria. Okay, so these are the big ones that you really need to walk away from this class knowing in and out, because you're going to use those in your design of machine components classes. Numbers 2 and 3, but also helpful to know number 1. But the interesting thing about all three of these particular theories that we've talked about at this point is they all sort of rely on the fact that the material will fail the same in compression as it does in tension, which is not always the case. Okay, so I'll say that these assume same fail stress in tension and compression. Okay, and that's not always the case with real materials. And you know this if you ever worked with like concrete, right? Concrete, amazing in compression, horrible in tension. Horrible, I say. Okay, so I want to just touch quickly on what is probably the most commonly used method for evaluating failure stresses of materials that have dissimilar failures in tension and compression. So we'll just talk about this quickly. And the main theory used to tackle this is called the Coulomb theory. Coulomb Coulomb theory. And this is generally for brittle materials that don't have the same failure stress in tension and compression. Okay, one example might be concrete, or ice is another one. Strangely. Concrete! Ah, exclamation mark. I don't know why I put an exclamation mark there, but ice! Ah! Maybe it's because winter's coming and I'm getting nervous about ice. I don't know. All right, so let's assume that failure in compression given by sigma naught here now with a superscript c, and failure in tension given by sigma naught with a superscript little t, as opposed to Mr. T. A petit fool. All right, and here's the failure criteria. It's pretty sort of like simple when you think about it. It's maybe a combination of the contribution that your largest principal stress makes towards tension, plus the contribution that your smallest principal stress makes towards compression, both potentially adding up to give you some failure criteria. So here's the equation, and I'll sort of talk through it. We'll say if principal stresses at a point given by our following sigma 1 greater than sigma 2 greater than sigma 3. All right, so we're ordering them in the traditional way, right? 1 is greater than 2 is greater than 3. Then Coulomb is first principal stress normalized by the failure of that particular material in tension minus the third principal stress divided by the failure of that particular guy in compression. If this together is greater than or equal to 1, you fail. Okay, this has flavors of like maximum normal stress theory in sort of a way. Okay, it's like, I'll say similar to. It's more similar to max shear stress theory. Which, if you remember, was like sigma 1 minus sigma 3 divided by 2, greater than or equal to sigma 0. On 2, you would fail. Remember, that's our max shear stress. Or if you simplify, sigma 1 minus sigma 3, greater than or equal to sigma 0. This was just like our general max shear stress theory, right? If you thought about like rearranging this equation by dividing both sides by sigma 0, you would end up with like sigma 1 minus sigma 3 divided by sigma naught greater than or equal to 1. Okay, so you think about this as like the difference in these principal stresses when normalized by the yielding stress. If that's greater than or equal to 1, you would fail, right? So we have flavors of that with our Coulomb theory, except we don't normalize this difference by one value. We normalize each of those individual components by the yield stresses in compression or tension, sort of see what happens. Okay, so this is similar to what we just saw for Coulomb sigma 1 over sigma naught tension minus sigma 3 divided by sigma naught compression greater than or equal to 1. It's very, very similar kind of concept or idea. If these values were the same values, it would simplify to your max shear stress theory, right? Okay. So hopefully we sort of see that. All right. Now, how does this actually look in your failure envelope? All right. Well, if we did like a sigma 1, sigma 3 here instead of sigma 1, sigma 2, which we had normally done, you might have a situation. I'm going to bring this down here. Or, okay, here is your maximum that you can handle, like in tension in both situations. So here's sigma naught T. Here's sigma naught T. But in compression, you can handle maybe twice as much, let's just say. Okay. So here, maybe twice as much, I don't know, down there. And here, maybe twice as much, maybe out there. So here, negative sigma 0 in compression. Negative sigma naught in compression. Right? So you would have something that looked like this. Okay. And this is your failure envelope for Coulomb. Oh, that's terrible. Gosh. I did not pass kindergarten. I cannot stay in the lines. So even though they gave me a PhD, they held me back because I didn't, pass kindergarten. There you go. That's better. All right. So we could see here generally that if, the amount of stress this guy can hold in compression is higher than the amount that it can hold in tension, we have a much bigger failure envelope down here in like a fully compressive state than we might have in like a fully tensile state. And when you think about like concrete applications, this is usually the case. And in areas where you need additional tensile support for concrete, they use rebar, obviously. Okay. So That's all I'm going to really say about the Coulomb theory. I'm not going to test you on it at all, and I'm not going to have any homework problems on Coulomb. I just want you to be aware of this particular failure theory that might exist if you have materials with dissimilar failures in tension and compression. Okay, so that'll conclude the failure stress notes, and we'll now move on to the next topic, which is buckling. And I'll survey the room since people are in front of me here. How many days did you talk about buckling in 2004? You can show me on your hand. 1 to 2. I'm getting the scissors over here. Do we have 0? 2? 2? All right. So at least you guys have seen it a little bit. Okay. All right. Good. Well, that's nice. I've had some 3005 classes where it's been 0. We did not talk about it, and that just like makes me a little scared. But okay, it is what it is. So new topic, buckling. All right. And I think this is my favorite topic for the course, personally. I think it's really quite interesting, and if people don't consider buckling for failure, then you're going to be a bad engineer. Okay. So long, slender columns under load can fail prematurely before you might predict with the failure theories we just talked about, right? And that's because of this like instability in long, slender columns. And I brought this ruler here because it's like the most classic example. All right. So you this before, you got this ruler, right? And if you like load it on the ends, it will like buckle, all right? And this material itself is not fail, it's not yielded, it's not fractured, it's not broken in any way. It's just, buckling. And this is just an instability in materials that exist in the world. It's just part of the physical world that we live in. And so if you're not considering buckling in a potential situation where it could occur, like if you have long, slender columns that are holding up a building, for instance, and if you're got a, that sort of column that looks something like that holding up a building, you're not considering it, your feeling's going to be a little wobbly, I'd say. All right, so not so good. All right, so we need to consider this. All right. So let me just write some things here as motivation. Long slender columns. Um, under like axial loading can buckle in an unstable manner. Okay. And the example I just used was like a long slender ruler. These can sometimes occur at loads that are significantly lower than that which might cause yield or otherwise cause the material to fail. Let's say that would normally cause failure by yielding. Let's just kind of stick to like yield metals for now. All right, and again, ruler is an example. It can be like sometimes way less. We're talking, 5% of what you might predict with maximum normal stress theory or something like that. Okay, way less. All right. You probably saw this in your 2004 class as the following equation, and I'm going to sort of review that quickly. Okay, did we all see this or something along these lines in 2004? Pi squared EI over L prime squared or L effective squared or something along those lines? Yes? Okay, I'm seeing some head nods and some deer in the headlights. Okay, so maybe 50-50. All right, so what we're going to do is we're actually going to go over how this equation came to be. Maybe you derived it in 2004, maybe you didn't. We're going to talk about it in pretty gory detail here because the derivation here becomes important. It becomes important to know because in this situation, this particular equation is for centrally loaded columns. And so what I mean by that is a load directly in the center of the axis of the beam, right? You could have a situation where your load is somewhat off axis, and we have to be able to know how to deal with that by modifying the equation that you see here. And so to do that, we really have to go through the full derivation so you understand kind of like where this comes from and how we might modify if you, for instance, have some load that might contribute some bending as well as some axial loading to that cross section. Okay, so let's do that quickly. The first thing I want to talk about is the elastic curve. In the elastic curve, there's a variety of definitions, but it's typically a function that represents the neutral axis of some bar. Okay. Question? Is that pi squared in the equation? Yes, Alan. It's a pi squared. Pi squared EI over L prime squared. Okay, I will continue. And so the idea that you want to have in your head, and you've probably seen this before, is that if you have like some beam, okay, and it's being deflected, I'll do the best I can to like draw some beam that's being bent. I don't know, something like this. Who knows? Right. Here's your beam. You got some pin over here, you got some roll over here, and this is being subject to some like force in the middle here, F. Right? You might represent this bar using just a general function, which we call the elastic curve. Okay? And that is, you could put like a coordinate system on this guy, maybe kind of emanating from the left-hand side here. Call this like X coordinate system. And, you know, this is typically like Y, or what you might see as V of X. When you're talking about like the deflection or the function that is the cross-section in the neutral axis of this beam. Then you might see this represented with sort of this elastic curve idea as like, okay, here's my support, my pin and my roller. I might represent this just using a simple line that looks something like this. Okay? So this is meant to represent the neutral axis of this particular bar. Okay? That's the idea of the elastic curve. And we typically say that this has a function. If this is x, x is the length along the axis of the beam, then we would call this v of x, or what you might call the deflection of the neutral axis of the beam. Deflection is the term. Writing the elastic curve allows you to do a lot of interesting things, like look at what is the derivative of this function, what is the second derivative of that function, and so on and so forth, and how those particular derivatives might be related to, let's say, the bending moment in the cross-section at any location, the transverse load in the cross-section at any particular location. So the point is this like elastic curve allows us to learn a lot of information about the particular cross-section and how it's related to like the internal moments. And hopefully you went through all of that sort of stuff in 2004. I don't have a ton of time to do it right now, but I want to say that like this allows us some very useful relationships. between, let's say, the slope of the beam, applied moments, deflection of beam, and internal transverse loads. Those relationships, which I sort of hope that you have sort of seen before, all stem from what is known as the moment curvature equation, or sort of the governing differential equation for a beam in bending. And we sort of talk about this in words, but in math language, which what we're all kind of familiar with, is what we call the governing differential equation of beam bending. So it's sort of a simplified version. And boy, I hope that you guys have seen this before. D squared Vx squared equals mx or EI. Okay. If this is not familiar to you, in the lecture notes, kind of like slides 2 through 5 of the buckling, there's a full-on derivation of this particular equation. All right. Hopefully this is not the first time that you've seen this. Okay. You can sort of play with this guy and take derivatives and take integrals and sort of look at various things. And we'll just do that here and say that the deflection of the beam is given by this function v of x. The first derivative gives you the slope. Okay. The second derivative gives you this like moment relationship. This is sometimes called theta x. Here we have EI d squared Vx dx squared is equal to the moment, internal moment inside of the beam. Another derivative will give you the shear load on the beam. And that is something like EIO. I'm just kidding. EI d cubed Vx dx squared equals Vx. Are we all having nightmares? This is a capital V, this is a lowercase v. And then finally, just the load. Beam. Might be this fourth derivative. Sometimes called F. Right. So this is kind of marching our way through sort of all the derivatives of that elastic curve given by V of x. How we doing? Can I get some like nods in the classroom? You've sort of seen this before. You haven't seen this at all before. Okay, get some nods. Okay, all right, good.
Hey, Dr. Hart.
Yes, sir.
Should the shear load on beam, the EID to the cube, like should that be dx to the third on the bottom?
Yes, thank you. There should be a cube here on the bottom, dx cubed. Okay, so all these relationships hopefully you've seen before and have worked with before. We're going to utilize these in part to come up with that critical buckling load formula. So let's do that now. And I want to first do this by drawing a picture. All right, so here we're going to derive critical buckling load. All right, and I'm going to sort of motivate this with a picture. And the beam that we have here is similar to sort of like the beams that you saw before, except we're doing this vertically instead of horizontally. All right, so consider an unloaded beam. So it just looks like this. Okay, and we've got like a sort of a pin-pin configuration. Let's just go with for now. Okay. Now we're going to load this axially. So you should see here now. Something that looks a bit like this. All right. Where we're providing some load on this guy. I don't have a ton of room to draw this, but here we have some load. Let's call it capital P. Okay. I'm going to put a coordinate system on this so that we can do some analysis. And that coordinate system will be starting sort of here on the bottom, top. Here's my coordinate system. Always along the length of the axis. This is the x direction. So then this might be the y direction. And here is x direction. All right, so this is the coordinate system. It's sort of a left-handed coordinate system, but let's just not worry about that for now. So the elastic curve on this guy, remember, it's like the neutral axis of the bar. Okay, so we're going to start at this bottom pin here, move to this upper pin, and this green line, this is your elastic curve, given by v of x. It's just a singular line of function. All right. What we're going to do here is we're going to make an arbitrary cut in the bar at some location x, and then do a force balance on that cross section. All right. So let's cut the bar. And you're going to end up with, here's your pin again down here. And your elastic curve, I'm only going to draw the elastic curve, looks simply just like this. Okay, and we've got our cut there at that particular location. At the bottom, we still have this force down here that's P. And now to balance out appropriately for equilibrium, we have a force balancing here P that is equivalent. And then we have some moment that we've generated that by relocating sort of this applied force, that here is this moment M, right, in this particular cross section. And we're going to say that this is at a location of x. Okay. And remember that this is our function v of x. Okay. All right, we're ready. The picture has been made. This is our cut at x. All right, so now we're going to sum the moments. And let's sum of the moments here equals 0. Okay. And that's simply going to be that this moment in the cross section, M at location x, plus P times the distance x equals 0. Okay, so maybe we're summing the moments about, I don't know, here, point O. So with our governing differential equation, not goddamn equation, governing differential equation, we have d squared v of x. Sorry, this is not x. This is vx is our length. Up here. Dx squared is equal to mx over ei. Okay, there's our governing differential equation. Okay. We rearrange that equation up there star as mx is negative p times vx, our moment arm. Then we have the following. Okay. Let's rearrange into standard form. All right. I'm going to make one more substitution here. We'll let, this will make sense in a second. Omega, this is the Greek letter omega, equal square root of p on ei. This will make sense in a second. Just hold it with me. Then our governing differential equation is d squared dx squared plus omega squared vx equals 0. This is a very commonly known and understood differential equation. Right. This is a differential equation for a simple harmonic oscillator. Maybe you talked about this in control. Have you guys had controls yet? It's in vibrations that you talk about this probably. Yes? You've had vibrations, haven't you? Have you had vibrations yet? No? When did you guys take vibrations? Or mechanical systems? Sorry, dynamic systems. Okay, that to me is vibrations. Okay, right. Okay, so you talk. Hopefully you talked about this in your dynamic systems class. This is like a weight hanging on a spring, and you release the spring, and it oscillates. Okay, same general equation, right? The equation of motion, except here now we have the equation of sort of deflection of a beam that's being buckled. All right. So this is equation 4, simple harmonic oscillator. All right. Whoa, baby, what happened there? Okay. So the idea here is we have this differential equation, and this differential equation is the equation that tells us what is that elastic curve of the beam given certain pieces of information that are contained in omega. Okay, so like if we load up the bar with a value of p, that's going to change obviously the deflection of the bar. If we have a different elastic modulus E, that's going to change how much you have deflection of the bar. If you have a different cross-sectional area moment of inertia, it's going to change how much deflection there is in the bar. So here now we have a governing differential equation that tells us, all right, if you modify these things, this is generally the relationship that you might expect for this particular bar. Okay, so if we have a differential equation and we sort of want to solve it, now we've got our governing differential equation. We also need a general solution, which is something that is sort of thought of over time, and boundary conditions. That's how we solve differential equations. So we need general solution for Vx and boundary conditions to solve. Okay. Well, you may or may not remember what the general solution is for a differential equation that looks like this, but most of the time, if you have a differential equation with like, you know, the function and a double derivative, you want to think of sine and cosine functions, right? Because the second derivative of sine is also sine. The second derivative of cosine is also cosine, just with signs flipped, right? So the general solution here is dx is equal to a sine omega x plus b cosine omega x. All right. You put that function into that differential equation, it will always be true. So if you just make a note here, the second derivative of this is something like negative a omega squared sine omega x minus b omega squared cosine omega x. So if you like punched all this stuff back into that original differential equation that we had, you would see that it would equal to 0, in fact, regardless of the terms a and b. For instance, if you put this guy in here, and this guy in here, you would get the answer of 0, regardless of the variable. Right? That's kind of the idea of the general solution for differential equations. All right, so once we have our general solution, which is here, we need to do something to figure out these capital A and capital B, and that is boundary conditions. Right? Now, if we think about what's going on with our particular beam, we can draw this. Okay. Again, here's our beam. Well, it's sort of like being deflected. Okay. And our equation coordinate system here is x and y. And let's say that this guy originally has some length of L. Well, there's a couple boundary conditions that are straight away pretty obvious. One here is that the deflection at x equals 0 is 0. Okay, so here's our g of x. First boundary condition would be that the deflection at x equals 0 is equal to 0. Okay, that's because we're pinned there. It can't possibly move in that like y direction. So that might be one initial boundary condition. Another boundary condition you might have is the same thing at x equal L, which is sort of the top of this beam. There's no deflection at the top of the beam in the y direction. No deflection at pins. You can sort of see that this function is equal to 0 at the top and the bottom of this system. Another thing that's a little bit more subtle is that the second derivative, or the moment, at x equals 0 is also 0. And the moment at x equals L is also equal to 0. That's because we have no moment arm length. Okay, Vx equal to 0, that means that the moment arm at that particular location is 0. Okay. This is also like the second derivative. Oh, I'm out of space here. Let's do the v double prime. V double prime x equals 0 equals 0, and also v double prime x equal L 0. Same thing. So we know the second derivative of this elastic curve is the moment. All right, so these are possible boundary conditions that we could use. All right, well, let's dive in on this. So let's look at boundary condition number 3 with governing differential equation and general solution. We know that our general solution looks something like a sine omega x plus b cosine omega x. Second derivative, let's label it as v double prime of x negative a omega squared sine omega x minus b omega squared cosine omega x. We already sort of wrote this. Now let's use boundary condition number 3 that says that v double prime at x equals 0 is equal to 0. Right? Let's plug that in. All right, the left-hand side, 0 equals negative a omega squared. Sine of omega times 0 is going to be sine 0 minus b omega squared cosine 0. All right, this is one of the bits of information, what are the boundary conditions that we can utilize to solve for what is this coefficient a and what is this coefficient b. All right, well, we see sine 0, obviously that's 0. Cosine 0, this is 1. So we're left here generally with 0 equals negative b omega squared. And we know omega is not equal to 0, so b has to be equal to 0. So this simplifies the general solution to Vx equals a sine omega x. Okay, that's where I'm going to call it today, and we'll figure out the last boundary condition when we come back on Wednesday. It will all be clear soon, I promise. That's it for today. Thanks.